Now we've got this circuit again. You're probably getting a little tired of it, but it's a really useful thing. And we're going to look at some other things that it does. In particular, we want to look at some different program states. So let me just list the program states we're going to look at. We're going to look at states in what's called the Bell basis. So we're going to look at the following 4 program states. I'm going to look at psi, capital Psi plus minus, and that is 1 over square root of 2 times 0, 1 plus 1, 0. So this is a BC. This is a BC. Okay, it's a plus minus. And the others are phi plus minus equals 1 over square root of 2 times 0, 0 BC plus minus 1, 1 BC. Now, since we've had a lot of experience with just tracing everything through the circuit, I won't bother doing it again. I'll just give you the answers. So what happens with these different program states? So let's look at, I'm going to put C here. And so that's the program state that we're going to put in. And suppose it is equal to psi plus. Now, if we work through things, that is going to be equal to, that will take psi to sigma x acting on psi. So what it does is, essentially it flips the 0 and the 1 in the psi state. So you put this in and it performs a particular operation on psi. If I make it psi minus, then what happens? Then the psi A goes to minus I times sigma y acting on psi A. So that's a different unitary operation acting on psi. And if I make it phi plus, then the psi goes to, now that one we actually did already, and that's the first one we actually did. It just goes to psi A. As I said, we already did that. We actually worked that one out in detail. And then if it's equal to phi minus, I get that the psi goes to sigma z psi A. So the sigma, just to be clear, sigma x 0 equals 1, sigma x 1 equals 0. Okay? And sigma z down here, 0 equals 0. And sigma z 1 equals minus 1. And for the sigma y, let me take a second. So the minus I sigma y acting on 0. So what you see what we've got here is we're able to control what the circuit does by putting in different program states. I can choose 4 possible operators in order to, and I can do that by putting in 4 different program states, and I don't have to change the circuit at all. So I can control what the circuit does by means of the program states. And you'll notice that what we've got here, and this will be important in a minute, that we have a 4-dimensional program space, and we have 4 possible operators that we can do. So then the question is, what kind of limitations are there on programming a quantum circuit like this. For example, suppose we wanted to do something like this. Suppose we wanted to be able to perform, say, e to the I theta sigma z acting on psi, okay? And we wanted to, for our program, contains theta. So we would control the theta by means of a program state. Now you notice if we do that, we're going to have an infinite number of program states. And well, can we get away with that? I mean, here we had 4 possible program states and 4 possible operations. Something like this would be asking for an infinite number of possible states coming out, for an infinite number of operations, and with an infinite number of programs, because each programs would have a different value of theta. So can we actually go from something like 4 to infinity without causing everything to go completely crazy? So what we're going to find out, thanks to Nielsen and Schwang, is that no, we can't. That doesn't work. So we're going to go through the Nielsen-Schwang no-go theorem, sometimes called the no programming theorem, which is a little bit of an extreme terminology. It doesn't say you can't program, it just places some severe limits on what you can do with a programmable circuit. So that's what we're going to talk about next.